so in this video we're going to talk about chemical kinetics along with the reaction coordinate diagram. Alright, so this is going to be one of the diagrams that is in the thermochemistry unit, but it also has to do with the kinetics. So what kinetics means is, or chemical kinetics, is a branch of chemistry that deals with the rates at which chemical reactions occur. The reason why it kind of deals with thermochemistry also is because we're dealing with energy. And we know that thermochemistry deals with the energy that is released or absorbed in a reaction. Okay, so the heat of reaction, which is delta H, is a difference in the heat between the products and the reactants. Delta H also stands for enthalpy. Alright? So the way that we would calculate delta H is the H of the product, so the heat of the products, minus the heat of the reactants. The unit that we use for this is kilojoules per mole. Alright, another term that we have to know is activation energy. This is the minimum amount of energy that is required to initiate a reaction. We can use the words big E, or the letters, sorry, big E, little a, in order to say that this is our activation energy. So in order for a reaction to actually happen, the particles need to have enough energy in order to get over almost like a hump. Alright, so it has to have a certain amount of energy, which is determined for each individual reaction, in order for the reaction to actually occur. A catalyst is a substance that changes the rate of a chemical reaction, and the actual catalyst is not altered at all. This down here, I know it's a little bit hard to read, it says it creates a new pathway. So the catalyst reaction, so the activation energy for that is going to be lower. It's still going to start with the same reactants and end with the same products. It's just going to be able to get there faster because when you introduce the catalyst into a reaction, you no longer need the same amount of energy to get that chemical reaction started. Okay, this right here is the reaction coordinate diagram. Make sure you take the time to write all this down and know what the different arrows mean. I know it's a lot and it looks overwhelming, but I'm going to go through what each of these are. But if you have to stop to pause the video to write all this down and then restart the video so that you can listen to me explain what each of these means, that might be helpful. Okay. So here, what we're looking at is an energy diagram, right? So in the beginning, we are starting with our reactants. Alright? Then at the end, we are getting to our products. It goes up and comes back down. This black line right here is the line that the pathway that the reaction would take if no catalyst was present. The amount of energy to get from the reactants to the very top of this pathway, that's called the activation energy, and that is for our forward reaction. So we're going from reactants to products. Okay, so once we get all the way up here, at the top of this loop, it is called the activated complex. So the activated complex is a substance that is created that's not our reactants and it's not really our products. It's kind of this in-between substance. No one knows what the activated complex for a chemical reaction actually looks like. It's just this substance that needs to be formed before you can get to your products. Okay. So the amount of energy that the reactants have before the reaction happens, that is called the potential energy of the reactants. Okay, so it's the amount of energy that those reactants hold in order to start a reaction. So we have our potential energy, then we are able to reach our activated complex if we have enough activation energy. Now we're at our activated complex. Then we start coming down. when we're coming down, this means that we are creating products. All right? So here we see change in H, which is the heat of the reaction, which I already told you was enthalpy. If we look at these dotted lines here, we can see that this space right here is the difference in energy from the reactants to the products. That is known as the heat of the reactants. Okay? If we look at this arrow right here, this tells us the potential energy of the products. So how much energy these products have after the reaction has been completed. All right. Now, so let's see. We've gone through the uncatalyzed reaction process. So here, this is the EA forward, right? And the EA of the uncatalyzed reaction, that's going to be our same thing as our EA forward. All right? Now let's go through a catalyzed reaction. So here, our catalyzed reaction is going to be this red one. If you notice, we are starting at the same point and ending at the same point, but we don't need as much energy in order for the reaction to actually occur. That's what our catalyst does. It lowers that activation energy for us. So if you look at these dotted lines, right here, that's the activation energy required with the catalyst. And we can write that EA cat. All right? What's really important to know with the catalyst is that the reactants and products are still exactly the same. It just takes a shorter time to get to those products. Okay, so everything that I've talked about right now, this is going from reactants to products. So this is known as our forward reaction. If I said that we were going in the reverse reaction, our activation energy reverse would be slightly different. If we were going this way, in order to get back over here, our activation energy reverse would be from here all the way up to here. So it would take more energy to go in the reverse direction than it would in the forward direction. All right, another thing that we have to talk about is exothermic and endothermic. I know I've already talked about both of these words. Okay, so when we're talking about an endothermic reaction, we are talking about a reaction that the products have more energy than the reactants did. When we're talking about an exothermic reaction, we're talking about a reaction that the products have less energy than the reactants did. Here, if we look at this diagram, our reactant started here for our energy. Our products are below that. That means our products have less energy than our reactants do. So this here would be an example of an exothermic reaction. If my products ended up higher than my reactants were, that would be an example of an endothermic reaction. Basically, what you have to be able to know for your test is how to read this type of diagram and be able to label the different parts. So EA forward, EA reverse, where your reactants are, where your products are, your change of heat of the reaction, your EA catalyst, your potential energy for your products, your potential energy for reactants, if it's an endothermic reaction, if it's an exothermic reaction. And then if you went back to the other side of this, we learned how to calculate delta H, and that's your energy of your products minus the energy of your reactants. So if I put a number here, say if I said that this was 400 kilojoules, and this was 500 kilojoules, kilojoules. If I wanted you to calculate delta H, what you would do is 400, so our product minus our reactant. So our overall delta H would be a negative 100 kilojoules.